Santosh, okay, so welcome everyone. I think today I will talk to you, tell you something about, or at least proceed towards ways of, at least some ways of producing magnetic fields which are self-sustained by turbulent motions in a wide variety of astrophysical objects. Okay, sun, galaxy, accretion disk, stuff like that. But what is the generic, at least one mechanism that could play an important role is something that we will try to cover. It's actually good to have some feel for numbers that exist in these type of astrophysical bodies. I've just taken things from, say, I think I'll come to you later for some references. On this page, it should have been there. This number of table is taken from a very nice review by Brandenburg and Subramanian, 2005. And whatever, in case you need to explore more, that's the reference you can look up. I'm sure that I would have given the references either later or otherwise I'll tell you in more detail. So as you see in the sun, for example, the typical temperatures are there, densities as you can see. More importantly, the control parameters are expected to be some sort of a dimensionless numbers. And the reason they are called control parameters is because various details might be irrelevant so long as the control parameters are same in two different systems, for example. Okay. In context to say things that we are going to talk about. Okay. Exact number is not very important for the talk, but you can see that stars like sun, for example, which have convective envelope. Yeah, not every star has a convective envelope. Yeah, it's only in the late type stars that it develops that the energy is transported mainly by convective motions in the outer layer. Some stars are fully convective, like M-type stars. Sun is like a G star. And you might have already been told about the various types of stars that exist. Point is the Prandtl number, magnetic Prandtl number, which is a ratio of kinematic viscosity divided by magnetic resistivity, which I have not told you yet in detail, but I did speak a little about the electrical conductivity. Inverse of that is basically the resistivity of the plasma, basically the reason that things will decay. If I have a magnetic field, it will suffer an ohmic decay, okay, over a period of time. Okay. So clearly something which is dissipative and you nevertheless observe, one should come up with ways of producing back the magnetic field. After all, the universe is very old and we are observing magnetic fields at all these scales. I hope it was clear from yesterday that the electric fields we normally don't discuss simply because there are charges, separate charges plus and minus, and they can short out any electric field, whereas this is not possible for magnetic field because there are no magnetic monopoles. Okay. You take the ratio and find the typical number, which is basically it goes as t to the 4. Basically, just take the ratio, and these are the typical numbers for the temperatures of order 10 to the 6. Okay, and it will rise steeply with this. For example, if you look at the galaxy, the Prandtl number is very, very large. Okay. Systems with very large Prandtl and other systems with very, very small Prandtl number can even be qualitatively different in their properties of, say, magnetic fields. Okay. It is likely because this is one of the very important control parameter. These are the typical speeds and sizes, but dimensionless numbers are more relevant. This is a magnetic Reynolds number. We discussed for the fluid Reynolds number. Similarly, from the induction equation that I'll come to, you can construct a dimensionless quantity which is a magnetic Reynolds number. And as you see, In astrophysics, these numbers are very large, very, very large. Okay. So they are typically very large numbers. In galaxy clusters, for example, you see 10 to the 29, at least some estimates. Galaxy is very large. All it means that the fields associated are extremely turbulent. Okay. Extremely turbulent. Analytical models have their own limitations to deal with turbulence, and people adopt various approaches and approximations to make some progress, or at least get some semi-qualitative idea of what might be going on in these systems. Okay. And these are microscopic quantities, okay, which will get updated in a turbulent motions, because all of this may not be relevant for the scale and dynamics that you may be interested in, and all of these quantities will get renormalized to something which is much larger value than these numbers. Okay. What is a dynamo? I have not very clearly defined. I'll also come to that, but roughly I told you yesterday that it is a mechanism of converting kinetic energy into the Santosh, can you Santosh, can you yeah, I request everybody to please be mindful and do not turn on and speak. It will be very disturbing. Okay. Yeah. Do it. Yeah. Otherwise, there is something towards the end. You raise hand and then, but yeah. Otherwise, just irritating. So okay. So fine. So if you, there are typical turbulent motions over a size of, say, where the energy injection is taking place. If you want to think of, say, a galaxy, then the typical energy injection for turbulence in galactic disk, think of a spiral disk galaxy. That is what I'm thinking in the moment. That scale is of the order of supernova scale. Okay. So, of order 6 supernova scale, say 100 parsec or something, a little bit larger than supernova. That's the stirring scale with the turbulent motions of order 10 kilometers per second. You construct a dimensionally a quantity which has dimensions of diffusivity. Okay, it's a turbulent diffusivity which has a dimension of length square divided by time. Okay, and if you construct such a number, just to give you an idea, this turns out to be 10 to the 26 centimeters per second. It'll be clear in one moment what do I mean and why do we need and stuff like that. So decay time of anything, any magnetic field that is there in the system, if suppose I give you a magnetic field in a system, dissipative system, magnetic field will decay. We want to estimate a rough estimate of the decay time scale. Okay, take a magnetic field which is a large scale magnetic field on the order of, say, scale larger than the energy injection scale. Already you see that we are thinking of large scale dynamo here, that the you inject energy at a small scale and magnetic fields are produced at a large length scale, and that's one mystery. How do you produce magnetic fields over large scale? Some sort of an inverse cascade of energy, that it goes from small scale to large length scale. Typically in a fluid turbulence, hydrodynamic turbulence that you might have heard before, you inject energy at some large scale and it cascades down to a smaller and smaller scales until it is dissipated by microscopic viscosity. Okay. Here we are thinking of an opposite problem. It's an inverse cascade. Energy is injected at a small length scale and is produced at a large length scale. Just think of your room and you try to stir the medium at the scale of your hand, and eventually you see that the magnetic field is produced over a scale of your entire room. Okay, so that's one way to think of inverse cascade and energy transfer towards larger and larger length scale. So dimensionally again, you construct for a given magnetic field over a scale length square and divide by the turbulent diffusivity. Yeah, take these numbers. You find a typical time scale of 10 to the 8 years. Okay. What is a galaxy's life? Spiral galaxy like that of our own Milky Way has a lifetime of about 10 to the power 10 years. Okay, so the galaxy has lived for at least 20 decay times. What does it mean? That any field, suppose somebody tells you that the galaxies were born with the magnetic field, suppose they are born with the magnetic field and they were not produced by a dynamo or something, but you know that now that any field that was present even at the beginning would have decayed in the lifetime of the galaxy. Okay, galaxy has lived long enough to kill any magnetic field that was present to begin with. Okay, but you observe magnetic field routinely, so clearly it motivates that we should have something to regenerate or produce the magnetic fields which is self-sustained by turbulent motions. Yeah, and so that the system is decaying and then producing and stuff like that, so that the magnetic field is maintained, and magnetic field is basically present at all times regardless of the system. Various astrophysical objects, you go to clusters of galaxies, you go to the voids, galaxy voids, everywhere, wherever people have observed, people have found magnetic fields. Okay, that calls for a need for it. We must be able to produce magnetic fields out of turbulent motions that are already present due to some other reasons in those systems, such as galaxy. Okay, so that I hope is clear why we need a dynamo. Okay, because otherwise the field will decay and you will not have magnetic field. But we do see magnetic field, so we must maintain it somehow. We must produce it somehow. That is the need for a dynamo. Okay, the tools for studying the evolution of magnetic fields have to come from the Maxwell's equations. After all, that is where the whole thing starts. That tells you the dynamical equations for the electromagnetic fields. There are these 4 Maxwell's equations that you have come across. I will not have too much time to go into. But yeah, they are magnetic fields, electric fields. This is divergence B equals 0. That's why magnetic fields are not shorted out. Absence of monopoles, magnetic monopoles. Then there is this current. Standard Ohm's law. Then you appeal to a model of relating currents with fields, and that is given in terms of standard Ohm's law in a fixed frame of reference in which the plasma can be in motion. That's the motional term. Okay. Yeah. And for more details, you please look up the reference I will show in detail later. That how do you think of it? But this is a model for relating the current, electric current, proportionality constant being sigma. Of course, if the conductivity is large, currents are large. Okay, conductivity is small or 0, there is no current. Yeah, very simple. If I just have an electric field, yeah, that also will drive a current. Now you just eliminate this J using this form and write down the equation in this way. Okay, that's the equation that you can write. It turns out that the resistivity in astrophysical settings are so small, very small, okay, that this entire term here, regardless of, and there is C square sitting. So this whole term is extremely small that any electric field dynamically will just decay over time in a time scale of order 10 to the minus 14 seconds or something. Now we are talking of time scale, say for galaxy 10 to the power 8 years, 10 to the power 10 years. So it's a very, very large time scales, okay, giga-year time scales. If something was there and decayed in 10 to the minus 14 seconds, that is clearly not very relevant for the present discussion. So we can just forget about this term. As you know that this is the displacement current term. Yeah, this is the post-Maxwell's equation essentially. This was the this term was not there, and most of you might have already learned about the history of this term, which is called the displacement current term, and that makes this whole setup consistent and correct. Okay, so you forget about that and write the electric. Yeah, that's called the Faraday time scale. Right? There is an electric field. There is a time here. This whole equation has a dimensions of electric field. Okay, this whole thing has a dimension of electric field. In these units, the electric field and magnetic field have the same dimensions. V by C is dimensionless. E has the same dimension as P. Okay, these are the Gaussian units in which eta is given by this. Okay, So clearly this gives you time scale eta by c square over which this term becomes important. That time scale turns out to be for ionized plasma 10 to the minus 14, and T4 is like temperature in units of 10 to the 4 Kelvin. That's the unit, that's how it is written T4, and that is known as a Faraday time scale. And as I said, if you take a plasma, induce a charge separation, charges will move towards each other because plus and minus will attract and they come towards each other, and whatever electric field was there, that will be shorted out. Yeah, all this will happen over time scale of Faraday, like this given here. So it's a very small time scale, given that we are interested in global time scales and giga years kind of time scale. So forget about the displacement current term. Okay, it has its own consequences, but for now, just forget about it. And you write whatever was remaining, which is the electric field. You see that the magnetic field is not independent. The electric field you are expressing now in terms of magnetic fields. Okay. So this is the term that you use now back in the this Faraday's law of induction. That's the Faraday's law of induction, that any curl of electric field will lead to change in magnetic field. After all, we are interested in producing the magnetic field, so we should aim towards a dynamical equation for magnetic field. By dynamical, one means how magnetic fields evolve as a function of time. So that is the equation. So that is the equation you want to ultimately look at. Just put back this electric field into that Faraday's law of induction, and you get a term like this. Okay. It so happens that eta in many cases you can take it to be constant throughout. So this grad will not hit this eta. So eta can be taken out like this here, and you write two separate terms, which is curl of B cross B plus eta curl of B. You use the divergence B equal to 0 will give you a Laplacian of B. Okay, that's for a positive eta is always a dissipative term. So if you don't have this term and you have del B by del T equal eta Laplacian B, just like your temperature diffusion equation. So that's a diffusion equation. This will give you an advection and other things like stretching and advection and stuff. But this term is basically these two will lead to a ohmic decay of any magnetic field. Okay, so over time this will decay. If eta is very small, of course the decay time will become very large, because decay time, even if you go for microscopic, then it will just be eta. So time becomes very large. Eta is small, so one may argue that in galaxies where the Reynolds numbers are large, eta is very small, then the decay time is so large, much larger than the age of the universe, then why do we need to maintain it? Because then, yeah, this field will survive over the lifetime of universe. Okay. Argument is, once you have turbulence, your eta here will be augmented by turbulent diffusion. So you should imagine eta as eta plus eta t. When eta is very small, eta t is still there, it's present, and that will kill the field in a very short time. Okay? In a very short time. This is a very short time compared to the lifetime of a galaxy. So please understand that this is 10 to the 8 years, sounds an enormously large number. It's a very small quantity compared to the lifetime of a galaxy, and that is what is relevant, that you have to maintain fields in these time scales. I hope this is clear. This equation is called the induction equation, the equation that we will need to evolve the magnetic field and see if the system supports a dynamo. It is not clear immediately if this supports a dynamo, but this is the equation that is the most fundamental equation to study the evolution of magnetic fields in a variety of astrophysical objects, and therefore it's extremely important, most fundamental equation. And whenever you hear induction equation, this is what one means. Induction term, diffusion term. This is the term that could in principle lead to the growth. This will always kill the field, but this may lead to the growth of magnetic field depending on the situation and circumstance or the nature of turbulence, you can say. Okay. Analogous to the Kelvin circulation theorem that we looked at before, if you look at it carefully, this is a quantity like what? It's a quantity like circulation. Okay. What was circulation? Circulation was omega dot ds over a surface. Okay. Now, if you look at the equation, in an ideal case, ideal meaning non-dissipative. So in an ideal non-dissipative case, this term is not there. You replace B by omega, these are the same equations, right? So the formula that you require to derive the circulation theorem will proceed exactly identically, and you will get something called magnetic flux freezing. Just like the vortices were frozen to the fluid, and consequence was that through any area element, the amount of vorticity flux that goes through is constant in time. Identically, you can show that in ideal MHD, which is eta equal to 0, yeah, the material derivative, the Lagrangian derivative of the flux, just like circulation, is also 0. It has very interesting consequence. That means I can write B times the area equal constant, right? B times the area, entire area. Yeah. Take, for example, for illustration, say star like sun. So let's say this is the sun. Eventually, sun will collapse and may become a white dwarf or some compact object. If I just take a star of size this, magnetic field starting with 1 Gauss magnetic field, and it collapses to a radius of 10 kilometer. Question is, what will be the magnetic field in this configuration? You have not done anything. There is no turbulent motion. There is absolutely nothing. It's a very clean system. You have a magnetic field, magnetic ball. It has a magnetic field of this order. You simply collapse the object and gone to a smaller and smaller radius. This theorem, you can write B1 times 4 pi R1 square, that's the surface area. That is the total flux coming out of this star, like the sun, for example. This is the entire flux coming out of the sun, and flux must be conserved regardless of what is happening to the body. It's a material derivative which is 0, right? So now these are the same fluid particles which have collapsed. So you will write B1 4 pi R1 square equal B2 4 pi R2 square. That will give you B2, that there will be a square gain in terms of the radius, and 1 Gauss becomes 10 to the 10 Gauss. So you see that just by the action of collapse and appealing to the magnetic flux freezing, you have actually increased the magnetic field by 10 orders of magnitude. It's amazing, right? A lot of people might tell you that this is dynamo, this, that. This is not a dynamo. Okay? This is not a dynamo. For a dynamo, you don't really require any collapse. Actually, the fundamental definition could be stated as, if there is a star or a body or any area element, if there is a net flux increase, that is called a dynamo. If the flux increase, right now I said there is no flux increase because of the flux freezing, okay, and it's a general enough proof, okay. But in a resistive plasma, you could be in a scenario where the fluxes could decay, fluxes could increase. Resistivity is extremely important, even if it is 0. So that's another example I gave last time. That nu equal to 0 and nu tends to 0 are qualitatively different, completely two different setups. Okay, Reynolds number going to infinity and Reynolds number is equal to infinity are not the same. Okay. Yeah. Similarly here, eta equal to 0 is very solution gives you like this. But eta tends to 0, which is very high magnetic Reynolds number, it's dramatically different, highly turbulent, dramatically different. Okay. So I hope this is clear that this is possible to, and any star, for example, you know that the pulsars have high magnetic fields. So of course, stars have collapsed, and as a process of collapse, the magnetic field will always increase because of the compactification of the object and appealing to the flux freezing, which is anyway going to be true to some extent. Right? Whenever you are squeezing the star, after all, the magnetic field will get intensified to maintain the certain flux. Okay. So let's just make me give you some comments on Magneto hydrodynamics, and you can read more at peace at home and through other literature if you are interested. Okay. So Maxwell's equations, having ignored the displacement current, is no more relativistic in some sense, and then This is a slower dynamics. Okay. So dynamics is such that the velocities involved are much smaller than the speed of light. Okay. So it's a non-relativistic limit of Maxwell's equation, the MHD. By MHD, one typically, whatever one means by MHD is somewhat continuous. Okay. It's a single fluid description. That means the charges are not separated. You're not talking of plus and minus charges. It's a single fluid. Plasma is modeled as single fluid, highly conducting single fluid. So while there is no electric field, the charges can move while maintaining the quasi-neutrality of the plasma, and then can drive the current, which is given by this. Charges, like electric charges, and this is plus charge, minus charge, charges in motion will give you electric current. That's all. That's as simple as that. This is a charge density. You can write down the Lorentz force. Okay, if there are electromagnetic fields, they will exert Lorentz force on the fluid, right? We have looked at the momentum equation, which is the Navier-Stokes equation with this new term. If there are forces coming from electromagnetic fields, that you just add. Just like gravity, we were adding like a body force. So if there are Lorentz forces acting on the fluid, which is a plasma in this case, this is V is a plasma velocity, or a velocity with a plasma particle. Now let's call it a plasma particle, but think in terms of just the way I described the fluid particle. Okay, it's a large number, collection of large number of particles. Important, and collisions are very important, and there is a local thermodynamic equilibrium. Only then you could write such quantities, thermodynamic quantities like pressure, density. Otherwise, what sense will it make to have a temperature? What does it mean? Yeah. So there is a local thermodynamic equilibrium, and that's a momentum balance that you can add another force. After all, this is acceleration due to all these forces. Okay, so it's as simple as that. This is just Newton's laws of motion. Okay. If magnetic fields are very weak, you can forget about it. And once you forget about it, while still dealing with a magnetic field evolution problem, this is called a kinematic problem. Okay, that is what we will also talk in a minute. Electric part of the Lorentz force is neglected as compared to the magnetic part. Okay, that's why there is only magnetic part here included. You can actually work it out. You take this part, you take this part, take the ratio between the two, and show that for yourself. That ratio of this term is of order V square by C square. Okay, that you can show explicitly. Okay, use all the usual conductivity equation, continuity equations, and whatnot, and you can explicitly show Ohm's law and stuff. You use the Ohm's law and everything. Order of magnitude estimate of ratio of this to this is of order V square by C square. We are in the non-relativistic limit, so V square by C square is extremely small quantity. Okay, so extremely small quantity. Okay. If we go to the limit eta 0, or we take, actually you just call it eta equal to 0 in the induction equation, that leads to the flux freezing. Just like an ideal fluid, this is our ideal plasma. In ideal plasma, the magnetic fields are frozen. All it means, effectively, is that if there are motions in plasma, every plasma element, you can imagine some magnetic field with the plasma element. Wherever that plasma element will go, it will carry the same magnetic field with it. So it's frozen to the plasma. That's why it's called frozen. That you take the plasma from one place to another within the system. Galaxy, there are rotations, there are stars, there are spiral arms, there are motions of plasma. Wherever the plasma goes, in the ideal limit, it carries the magnetic field with it. It doesn't slip through the plasma. Slipping is important in reconnection and that kind of thing. Once you set diffusion, that is what is happening. The magnetic field can diffuse through the plasma. Okay, but in this limit, when there is no dissipation, then of course this is frozen to the plasma and that can just move with the plasma. If I set velocity, which can have large scale component, small scale component, I'm not specifying anything. But if there are no motions, then this term doesn't rise. This term just goes to 0. If this is 0, then this is simply a diffusion equation, right? And then any magnetic field will just decay due to diffusion. Very important to note that it's a linear equation in magnetic field. There are no non-linearity in magnetic field, or you can say that there is no explicit non-linearity in the problem altogether. Implicitly there is the non-linear term such as in Navier-Stokes V dot nabla V, but there is a product term V cross V. In many ways, the product is as bad, or bad meaning complicated, I mean here. After all, it is that which is giving you all the interesting physics, so it's a very good thing. But I'm saying in terms of dealing with the equation, it is as complicated, nearly as complicated as the non-linearity itself. So while the equation is linear in B, it is not simpler. Okay? That is the point. It's not a simple equation. All the magic that you see has actually essentially come and driven from this equation. Okay. But if you have V equal to 0, of course there is no induction. If B was 0 to begin with, you cannot evolve this equation. Okay. This equation will not evolve. That means if B was 0 at time t equal to 0, it will remain B equal to 0 at all times. So in order to maintain and evolve a magnetic field through this equation, you always will require a seed magnetic field. Okay. So that's the problem of seed magnetic field. There are many ways to produce seed fields, which I will not get into. Just imagine that galaxy was born with some very weak seed fields due to some other processes in the early universe like magnetogenesis and stuff like that. Okay. But in case the B was 0, that induction equation will not evolve to give you any value. So you always require a seed magnetic field, so that now turbulence can take over and may in principle produce the dynamo action. Formally, you should define dynamo as a conversion of kinetic energy into magnetic energy without any electric current at infinity. What does it mean? I can have a magnetic field at my site simply by driving currents at the boundaries. Suppose something is maintaining a current, and you've all learnt of Biot-Savart's law and everything, that if there are currents flowing, that current will have an equivalent magnetic field. Dynamo excludes that option. Okay, it should be self-sustained. It should be produced by motions within the system, not by an external currents that could be circulating the galaxy, for example, or hypothetically you can imagine. That is not allowed within the definition of dynamo. So it should all come from within. It should be self-sustained. That's the main criteria for a dynamo. The only choice you have basically is the velocity field, because the other term is dissipated. The only choice to grow or generate magnetic field is the flow V. So this acts as a dynamo. The flow, the plasma motions, this acts as a dynamo. Okay, it's a motion associated with a plasma particle. As you see that this is a linear equation. If you have an equation of the kind, think for a scalar, dx by dt is some coefficient times x. Yeah, this is always a exponentially growing or decaying solution depending on the sign of that coefficient. So if I have dy by dt equal alpha times y, solution is e to the alpha t. Y will go as e to the alpha t. You can imagine. If alpha was positive, it will grow. If alpha was negative, it will decay. That's as simple as that. Fine. That's a momentum balance. This is just an image. If you see a galaxy, there are lots of model fittings. Look at references. Whole galaxy is bright and synchrotron. And once you do all that model and everything, you find that there are magnetic spiral arms. Magnetic fields have a structure which looks like a magnetic spiral covering the entire galaxy. It's such a large scale magnetic field. Question becomes even more interesting now, because you don't drive motions at these scales. Motions are at a very tiny scales compared to these, which are basically stirring the fluid, stirring the plasma, in this case primarily by the supernovae explosions that are happening all over in the material arm. Yeah, there is a material arm, there is a magnetic arm, which need not be co-spatial. In fact, they are not. It turns out, it seems. So in these spiral arms, there are stars forming, there are supernova explosions, and for a lifetime of a galaxy, this is just like an event that is happening randomly all over the galaxy at all time. there are one supernova event in every 70 years or something, right? I mean, typically for my Milky Way, I think the estimate will be somewhere around one supernova in every 70 years. Okay, that is roughly the rate. Okay, suppose this is given over a time of galaxy or over the time of say mega year. If you watch like a fast forward movie of this galaxy, you will find that supernovae are randomly being produced or exploding in various parts of. So it's like a turbulent motion is being excited from all over. All right, and that is inducing that flow, which may act as a dynamo. Okay, and then one hopes that because of that driving or energy injection at such very small length scale, somehow this very coherent, large scale, smooth magnetic fields emerge due to the action of turbulent dynamo at a much smaller scale. I hope this argument is clear. Nowadays, one tries to simulate such a thing, and there is this review you could look up. This is just an update on a previous review just by Brandenburg and Subramanian in 2005, and this is the latest on that, which will tell you far more details than we can cover here. But the point is, you start with a cubic box, you inject energy at very small length scales, solve induction equation. These are colors indicate the magnetic fields. Only the Z component of the magnetic field is shown here. So, as you see at early time, the magnetic fields are like a very small scale magnetic fluctuations that are present. Very small magnetic fluctuations are present at very early times. Okay. This is what you see. You just proceed in time as a function of time. Eventually, you see that whole box filling magnetic field has been presented. It's a Beltrami field. Yeah. There is also a small scale dynamo, small scale magnetic field, large scale dynamo, large scale magnetic field. So dynamo has two classes, or people like to study them as two separate classes: small scale dynamo and large scale dynamo. A small scale dynamo meaning when the dynamo or magnetic field is produced at scales of order or smaller than the energy injection scale, then you call it a small scale dynamo. If the magnetic fields are produced at scales much larger than the eddy scale or the turbulent scale, then you call it a large scale dynamo. So magnetic field at super eddy scales are produced by the large scale dynamo. But you see that as a function of time, you've generated very large scale magnetic field. You are injecting energy still at a very small scale. So this is very routinely seen and done in simulations. Okay. And this one thinks may be relevant for galaxy. How do we study this? How do we produce magnetic fields on large scale? So we need to have an evolution equation for such a large scale magnetic field now. So I'm just going towards motivating for large scale dynamo. So that means we should be able to separate the large and small in some way. So what one appeals to is the so-called mean field theory. Mean field is much more slowly varying both in space and time magnetic field. The slowly varying component of magnetic field you can imagine as mean field. And by slowly one means both in space and time. Okay. So I take a total magnetic field. Prime here denotes total. So total magnetic field I can write in terms of mean plus a fluctuation. Okay. Mean plus a fluctuation. Similarly, the total flow can be separated as mean plus fluctuation. For example, the galaxy has differential rotation. So you can think the whole differential rotation is like this mean flow, and this is a turbulent flow which is deviation from that background. Okay, that's a fluctuation. Criteria for that is that if I take an average, which is and it obeys certain rules which are given here. I'll not go in full detail of these averages, but you look up Reynolds averaging if you are further interested. If I take average once or twice, it doesn't matter. That's the important criteria for Reynolds averaging. If I take an average, I get a mean field. If I take an average of fluctuating field, I get 0. Okay. Now this you can think for now as an ensemble average. What is an ensemble? This V, small v, is a turbulent component. Okay. So this you think of ensemble as a set where each member is a different realization of this turbulent field. Okay. So it's just a set. Ensemble is like a set where each member is a different realization of the flow. And if this is a turbulent flow, if I take an average over all these realizations, you get 0 for this magnetic as well as velocity similarly. And whatever remains in this process of averaging is what you call the ensemble average or mean field, ensemble average magnetic field. Now these are the rules that if you have already once mean multiplied with a fluctuation, and if you take an average, this mean you can take out, and then the average of fluctuation is 0 from such a law, and then gives you a 0. Similarly, if you have Reynolds average allows you that if you have to take an average of the entire derivative, like partial space or time, this you can slide inside you take inside the derivatives, and then you can write del B by del T. Okay, so these are the rules of Reynolds. Apply these techniques to the induction equation, you will get 2 equations, one for the mean field and the other for the fluctuating field. Okay. After all, we want to produce the magnetic field from turbulent motions, so we should see if, what structure we get for these field equations. So work out, you will have of course to work out in this term for total, imagine primes here now for total. So write for, or you write total here, E total cross B total, take an average of that term. So work it out yourself. You will get basically 2 terms here. Okay. One entirely made by the mean fields, mean velocity, mean magnetic field, and the other term which I have highlighted in green, that is the most important term for dynamo, for large scale dynamo, is entirely made up by turbulent motions or turbulent magnetic fields at very small length scales compared to this scales. Scales of these capital V and capital B are larger. Scales of this small v and small b are much smaller. Okay, but if you work it out, a mean of this quantity, you will get a correlation between these fluctuating fields. You can have fluctuating fields, but their correlations can have very large length scales and time scales. Okay? It is that which is very important. Okay, so now you take the large scale induction equation. You of course have just taken the average of that equation. You get this. Forget about this capital V term. I can just ignore the mean flow in the system. Suppose I don't have any mean flow. So forget about this term. Okay, it's just written for completeness in case you are intrigued. So, but forget about it. Del B by del T will again have curl of which we call a mean EMF, mean electromotive force or turbulent electromotive force, turbulent EMF, which is made entirely of the fluctuating quantity. So that is the source for the mean field. Now this mean field at least has a possibility, at least you can imagine now that I can grow the mean magnetic field solely by the action of small scale fluid flows and small scale magnetic fields. Of course, it's an average quantity, but after you have taken the cross product. Okay, so there may be long range correlations in these fluctuations. Okay, so that is the called a dynamo term. Okay, this is called the turbulent dynamo term. This is again as usual the dissipative term, which we eventually will forget about for the now. But as you also see, in order to solve for this mean field equation, this is a source. So you must know the source, right? Source involves small v and small b. Suppose I take a kinematic approach in the problem for which you can imagine that this small v is given. Suppose I just give you a turbulent motion profile and I declare that this is given to you. So this is known, but this is not known. So how do you solve for this? So then now you need to know an equation for this small b. But that's very simple in the sense you take the total induction equation from which you subtract this mean field equation, then you get an equation for fluctuating field. But now you run into a usual problem of turbulence, this turbulence. Then once you write down this, there was this E sitting here, right? Once you have subtracted, this has not gone, this has come here. So in order to solve for capital B, you need EMF. In order to solve EMF, you need small scale b, and in order to know the small b, you need again this source. So how do you go about it? So that is called the usual problem of closure. It's a closure problem. There is an infinite hierarchy of terms. If you just go on expanding, you can show that there are infinite hierarchy of terms that you will need to solve in order to actually come to this. So that's a closure problem, and that makes the life very, very hard. And that is coming because of this product term. So product, in that sense, I mean, is as complicated as your non-linear term. Okay. So it is non-linear. It is linear in magnetic field still. The whole equation is linear in magnetic field, but it is non-linear in fluctuations. So it's non-linear in fluctuations because there are one fluctuation, another fluctuating quantity. Two fluctuating quantities are you've taken a product. So it's a problem of turbulent dynamo is basically involves non-linear interactions in fluctuations. Okay. I hope this point is clear. What one now does, typically, I've highlighted this whole term as green, as a first order smoothing approximation, because we still nevertheless want to make some progress. We are desperate people. So this small b, we can only solve if we didn't have this term in the simplest case. So we forget about it. So this is ignored so that you only have 2-point functions like v type function. If you don't do that, you will have infinite hierarchy that correlations can be VV, and then you substitute back for B in terms of VB, and then you have VVV. So basically 3-point functions, 4-point functions, 5-point functions. So you have infinite hierarchies of functions, but you want to stop. It's like having a series solution and truncating at some lowest order. So this is a truncation in which you simply ignore this term and try to argue what still nevertheless can give you a large scale magnetic field. I hope this point is at least clear. So it poses a closure problem, but we will deal with this in so-called first order smoothing approximation, for which you forget about it. Then you see that you forget about this capital V as well. This also you can forget about. This eta is very small. For a very simple argument, you can say that, okay, this is small term, you forget about this, forget about this, forget about this. So all you have is V cross small b. Small b you can write as integral, time integral of this term only. Small v cross capital B. So I can imagine that this will give you V cross B, capital B. Now average, the capital B you can take it out. So this will have a structure which is of 2-point velocity correlate. I think structure you can just see from this here. And once you know this, then you can of course use it and solve this. What I mean to say is that the mean EMF is simply depending on the functional of mean magnetic field. So you can write this in a very simple language that mean EMF is written in terms of mean field and its derivatives, where these coefficients are entirely made up of turbulent motions. Okay? So all the effect of turbulence has gone into the so-called turbulent transport coefficients. Okay? All these coefficients that you study here, these are what? These are transport coefficients. Right? These are microscopic transport coefficient. This is a turbulent transport coefficient. Now you have another here, alpha, which is another turbulent transport coefficient. It's a turbulent transport which governs whether or not field will decay or grow. You can solve that this so-called alpha, and you will very famously hear that one of the key ingredients to produce magnetic field in the universe in various contexts, cosmic magnetic fields are typically maintained, supported, produced by alpha effect. This is the alpha effect, which in this kind of approximation you can write some correlation time of turbulence and average of this quantity V dot curl of V. Curl of V is rotation, vorticity. If you take V with a curl of V and take a dot product, it leads to essentially a screw-like motion. It has a handedness. It can be plus or minus. Okay, like cyclones, right? So this is exactly like a cyclonic motion. And if on average this is non-zero, this is the term that can give you dynamo. This term will again dissipate or dissipate the field faster. Eta t is generally depending only on the energy density of turbulence. And this term is much larger than the microscopic eta. And once you write down the equation, of course, you will see that small eta is irrelevant for this discussion. And eta t governs the decay, which is very fast decay because this eta t is very large. but this term can actually produce back the magnetic field. So there is no problem perhaps. This is called kinetic helicity term. This is the helicity in the turbulent motion. Why we need this? I'm running out of time. I don't know how much. Okay. Anyway, so why do we need helicity in the system? Simple reason is magnetic field. You work it out that, or think about it, is not a normal vector. What is a normal vector? That it obeys a certain law if you look at it in the mirror. Okay. Magnetic field is a pseudo vector. It's non-mirror symmetry. It's a pseudo vector. It's not a normal. It's not a true vector. So there are, you know that there are true vectors and there are axial vectors, pseudo vectors. Okay. Magnetic field is a pseudo vector. Flow by itself is a true vector. So it's a topological question that if you have a true vector, can you produce a pseudo vector? The question is, can be framed in this way. If I'm given only true vectors in space and time, if I have only a true vector, can I produce something which is not a true vector? Answer might be most likely no. Okay? Just from the very topological type argument, you have to break the symmetry somewhere to go from true to pseudo. Okay. Now helicity breaks that symmetry naturally. Where can it be produced? Just like in the Earth's atmosphere. There are cyclones in the north, anticyclones in the south hemisphere. Okay. Why is that? Because of the Coriolis forces. Okay. So it will have one sign in one hemisphere, the other sign in the opposite hemisphere. Given that most systems have such geometry, you can imagine that this alpha effect will survive in each hemispheres, like with a cyclone and anticyclone. Any system which have rotation and stratification, they will tend to produce turbulence which will have a finite helicity. Helicity, you can imagine a motion which is a screw-like motion. Okay, screw-like motion. As it is rotating, it is also rising or falling. Okay, that is why you have non-zero dot with a curl of v. Typically, you can imagine curl of v can be a vector which is perpendicular to v, so that v dot curl of v is 0. Yeah. But if it is non-zero, then it's basically, as it is rotating, it's also rising up or down. So that is where you get a screw-like motion. Okay, it's never like in a plane. It's fundamentally a 3D quantity. They have rotation with rise. So it's a fundamentally 3D quantity. So think about all this topology of the flow and the nature of magnetic field and why you need to break the symmetry. This is called a mirror symmetry breaking of turbulence. Depends on the kinetic helicity of turbulence, and that is typically known to be the source of magnetic fields in a whole range of objects. Like the sun has an alpha, galaxy has an alpha, various such systems, they have an alpha effect, and most people think that this is the reason that we have large scale magnetic field. Okay, and it's an ongoing, outstanding area of research. People are still working on that, and the tough problem is not solved. But there is a great progress that has come in the last decade or so, in some decades or so last. That's a reference I meant earlier, that for much more detail and for a complete analysis of what we know is covered very nicely in this review by Axel Brandenburg and Kandaswamy Subramanian. He's a professor at IUCAA, and that's appeared in 2005. Okay, so I hope this is clear that in principle, just by having turbulence, this will sit as a transport coefficient here. You could drive and produce a mean magnetic field. Okay, that was only the point. That was all the point. I'm not going into the details of how alpha effect is produced. Okay. As I said, invariants play a very important role in producing and maintaining the magnetic field. One such invariant I will just mention is called magnetic helicity. It's a topological invariant. If I take two magnetic field lines which are interlocked magnetic field lines has a finite magnetic helicity, whatever you do with the magnetic fields, change it apparent topology and it looks different, it turns out that whatever you have done with magnetic field and produce a small or large scale magnetic field, this quantity turns out to be invariant in ideal MHD, regardless of turbulence. There is turbulence, but if you write down the evolution equation, you will find that this goes resistively. This decays resistively, or this has a resistive profile. But this is very small for the astrophysics. Eta is extremely small. Plasma is highly conducting. So dH by dt is nearly 0. So H remains constant. That is the point. This A is a vector potential, curl of which gives you the magnetic field. Okay. So all this is very clear. So I will not describe in detail the phi 1, phi 2, these are the fluxes. Flux you imagine in terms of magnetic field going through a cross section and stuff like that. Just read up some of these books and papers. The whole point is that one prediction is that you started from suppose zero helicity, zero magnetic helicity, because there was no linkages, knots, or fields were very weak. And now over a period of time, you saw that. So at this stage, suppose there is no net magnetic helicity. Magnetic helicity is also signed quantity, plus and minus, and you produced a large scale magnetic field, which is a Beltrami type field, which has a finite helicity of say sign +1. Suppose this, in the end you got a +1 helicity for a large scale. We know that we could not have produced magnetic helicity, net magnetic. So it must have also produced, that's a prediction, that if you see such a large scale magnetic field, you must have an oppositely signed magnetic helicity at a much smaller length scale. So you can have a spectrum of magnetic helicity with plus sitting at large scale, minus sitting at a small scale. In the net sense, net helicity remains 0 at all time of evolution, unless there are fluxes, and those are the details I will not get into. But in the closed boxes, you start from a 0 magnetic helicity. Whatever is the process working to produce and give you a large scale magnetic field, at no time you have produced a magnetic helicity in a net sense. So once you observe something with a plus magnetic helicity, you must imagine immediately that there is an oppositely signed helicity sitting somewhere in the system. That means that the field should always be, magnetic fields that are produced should always be bihelical. One sign on some scale, other sign on some other scale, so that plus and minus will cancel out to give you no change in the magnetic helicity. It's nearly conserved for even very high magnetic Reynolds number systems. Even when there are reconnections allowed, reconnection you would have heard, that is what is dissipating the magnetic fields, giving you X-rays, flares and whatnot, hitting the corona, maybe solar corona, all these problems you must have heard. Even in such cases, it turns out that the helicity changes by very minimal amount or nearly conserved, even when there is a finite resistivity. So long as it is small, it seems to be still conserved. This is a paper where it's demonstrated in paper in Paria. After all, and in this review, you will find all of this. This review covers every aspect of Dynamo pretty much in great detail. Okay. So it was recently tested in solar constant. So this can be an effective tracer of the origin of magnetic field. This was recently tested. Some of us participated in the study and tested and found that the solar magnetic fields were indeed bihelical, and that observationally shown bihelical magnetic field then becomes a proof in some sense of the alpha effect that is operating, because there is no direct measure of the alpha as such in the deep interior, because interior of the sun we don't see. But if you see the magnetic fields that are bihelical, that can act as an effective tracer on the origin of magnetic field. So this is the problem of origin of magnetic fields in the universe. You choose your system, pretty much you will land up with equations like these. And this being a pseudo vector, as I said, that this is a non-mirror symmetric object. Like if you have a left-handed screw and you see that in a mirror, you will see that the handedness of the screw has changed. Left-handed becomes a right-handed in the mirror. That means the mirror symmetry is broken in the turbulence. It is a pseudo-scalar. In general, these are very complicated objects. It's a tensorial object, alpha ij and eta ijk and stuff like that. So these are tensorial objects, very complicated. But in a very isotropic turbulence, very isotropic simplistic settings, you could write and express them in terms of kinetic helicity and energy helicity. This may act as dynamo and give you those large-scale magnetic fields that we motivated here and here. So I think I'll stop here and take questions. And so this was the reason. I think most likely, like in the sun here, these magnetic fields, ultimately the origin of these must come from that induction equation. That is the claim. So thank you. And this is the last lecture. And if you have some questions, I'll Santosh, if you are there, can you enable them to unmute and talk? Okay, there is one question I see in the magnetic contour images. Why are there contours with no apparent visual component in the picture? Okay. Why do you need that? Magnetic field can live in the free space also, right? You can have magnetic field in the vacuum also, isn't it? So why do we require a visual component for a magnetic field? Sometimes suppose that's an optical image. Maybe there may be a plasma, but it's not bright enough in optical image. But maybe you see it in X-ray. There is something. Yeah. So that is just a visualization, yeah, that one has put in an optical image over which a contours of magnetic fields. This by itself should not surprise you. You can have magnetic field in the vacuum. If we consider a plasma with no vortices, if we have okay, and low Reynolds number, will its magnetic field still dissipate over long term? Yes, of course. I mean, you need vortices in turbulent flows. Vortices are like building blocks of turbulence. They are always there. But if you do not have anything to maintain, as I said, if you don't, just having a flow and that too even a turbulent flow does not guarantee you a dynamo. Even alpha effect does not guarantee you a dynamo. Alpha effect has to be strong enough to compensate for the turbulent decay. Turbulent decay is happening regardless of alpha or not, right? So it's a very right fine balance that one has to find. Okay. And if not, then of course it will not be there. It will decay. It turns out that most systems do have magnetic fields. Somehow the systems like it. Will its magnetic field dissipate? Yeah, I'm saying that not only and in this case it will decay. It may decay even when there is an alpha effect. Alpha effect has to be strong enough to lead to growth. Any other question? If you have questions, just unmute yourself and ask. Okay, yes, Subrata. Hello? Yeah, I can see your hand. You can just unmute yourself.
Okay. Am I audible now?
Yes.
Yeah. Okay. I was wondering about this large scale helicity and small scale helicity. Then if you have a large scale helicity, then small scale must be there because the helicity has to be conserved.
Yes.
Okay. But then do the helicities carry any energy with them, right?
Well, energy is energy, helicity is helicity. It's after all the same magnetic field. It's helicity is like a configuration of that magnetic field. You can think of it like some twisted magnetic field lines. So helicity is a measure of that twist. Okay. And of course, that magnetic field has an energy density, say b square by 8 pi or something. So if there is a magnetic field, there is an energy.
Okay, all right. No, basically, I was thinking about how do these helicities also will have a time scale, right? The small scale helicities will be there and they will dissipate through time. So do they or not? And when how do those
you could better way to think about is a magnetic field. Suppose you take a decaying system, magnetic field is decaying.
Right.
Even while decay, it should maintain its helicity balance. So yes, of course, it will go down. There is even something called realizability condition. That if you have a helical magnetic field, the decay rate is slower. The magnetic fields will decay slowly, and of course, the associated helicity, the absolute values of those will also go down.
Okay.
But all it means is that more than the absolute numbers, the sign is important so that you are not producing any net in the process, decay or growth otherwise. Yeah. Absolute numbers will change, certainly. Yeah.
Okay.
Anybody else? Okay, if not, then I'll just wait maybe one more minute. And if there is no question, wish you all very good luck.